In this video, we discuss what it means for a function to be increasing, what it means for a function to be decreasing, and the first derivative test. So here are our definitions. We say that a function f is increasing on an interval I if for all x1 and x2 on that interval, if x1 is less than x2, then f of x1 is less than f of x2. So if I'm graphing that, that just means if I choose an x value to the left of a different x value, the corresponding y values go up as you go from left to right. So f evaluated at x1 is smaller or less than f evaluated at x2. And that's true for all of the x values in the interval. So as we're going along that interval, the entire time the y values are going up. So you just look at the graph, you look at it as you're going from left to right, and you say if the y values are going up, that function is increasing. Now, if I graphed the tangent lines at any of these locations, the derivative would be positive there. So this is the formal definition of increasing on an interval I. But one way that we determine whether a function is increasing on an interval is we look for that first derivative. And say if f is increasing on I, then f prime of x is positive on I. Because all of our tangent lines are going to have positive slope anytime our function actually behaves that way. Now we say that our function is decreasing on an interval I if the following is true. You pick an x value, and then you pick an x value to the right of that. If for every x, x1, x2 that you choose in the interval I, the first y value is larger than the second y value, then we say the function is decreasing there. So as you go from left to right, the y values go down. And so that's an example of a function that's decreasing. Now that is the formal definition of being decreasing on an interval I. But if we look at the tangent lines at each of those points, all of those tangent lines are falling as you go from left to right. So they all have negative slopes. If they all have negative slopes, that means the derivative is negative. So if f is decreasing on I, then f prime, which is the derivative, which is the slope, is negative on that interval. Okay, so making sure that we understand the concept, let's look at this graph. The question says, determine the intervals where f is increasing, determine the intervals where f is decreasing. Well, the function is increasing anywhere where the function just goes up as you go from left to right. So we start here at x equals 0, y equals 0. And as we go to the right, the y values are increasing, the y values are increasing, the y values are increasing until we get to this relative max of x equals, or excuse me, y equals 8 when x is equal to 6. And then the y values start to decrease. So our y values are decreasing, our y values are decreasing and decreasing until we get to x equals 8, y equals 5. And at that point, the function starts increasing again. We go from increasing here, and then the y values are decreasing on this last one. Now, when they ask us to determine the intervals where the function is increasing or decreasing, what they're asking for are intervals of x values. I think sometimes it feels obvious to me, but it might not be obvious to a student. We're talking about the intervals of x values that correspond to increasing y values. So we say, okay, well, what are the x values on this first interval? Well, our x's started at 0, and they ended at x equals 6. So the function is increasing on the interval from 0 to 6. And then it's also increasing over here on this interval from this point to this point. The y values are going up as the x's go from 8 to 10. The function is decreasing on this interval. That's x equals 6 to x equals 8. And then it's decreasing on the interval from x equals 10 to x equals 12. Now we didn't show any constant values, but if the function happened to be constant, like maybe it looked like this, from let's say 12 to 16 or something like that, you might say that the function is constant on the interval from x equals 12 to x equals 16. In that case, the derivative would be 0. So we know that our function is increasing on these intervals. That means f prime is positive on those intervals. It's decreasing on these intervals. So f prime is negative on those intervals. And it's constant on this interval. So that means f prime is equal to 0 on those intervals. Again, we know that because if I draw a tangent line at each of these locations, they're going to be sloping up. The y values are increasing as you go from left to right. So all of those tangent lines have positive slopes. So our f prime is going to be positive. If I draw tangent lines here, all of my tangent lines will have negative slopes. So f prime will be negative. And here my tangent line has a 0 slope, horizontal. Since the slope is 0, the derivative is 0. Okay, so this is going to, understanding this concept, this relationship between the derivatives and the intervals where the function is increasing, decreasing, or constant, allows us to graph functions even when we don't know what the function looks like. So we'll do a couple of examples. And here's our first example. I always like to start with a polynomial. Let's say y prime, or y is equal to x cubed minus 6x squared plus 15. Our goal is to find the intervals where y equals f of x is increasing, and similarly to find the interval where y equals f of x is decreasing. So most of the time our function is going to increase some of the time and decrease the other part of the time, like we have here, increasing, decreasing, increasing, decreasing, and then constant. So we're just trying to find those intervals for this particular function. Well, we can find those intervals by first computing the derivative and then looking at where the derivative is positive, negative, or 0. So first I'll compute y prime. The derivative with respect to x of x cubed minus 6x squared plus 15. The derivative of x cubed is just 3x squared by the power rule. Then we subtract 6 times the derivative of x squared. That's 2 times x. So the 1 less power, which is just 2 minus 1 is 1. Plus the derivative of 15, which is 0. So we've got 3x squared minus 12x equals y prime. Now that derivative is equal to 0 at a couple of different x values. Now we're interested in those x values where the derivative is 0, as those are critical points. And the critical points are potential locations where that function could change from increasing to decreasing. If the derivative is 0, it might be positive on one side of 0, or positive to the left of that point and negative to the right of that point, or vice versa, or it might be positive and then 0 and then positive, or negative and then 0, then negative. There are lots of possibilities. But the first thing that we do if we want to find the intervals where the function is increasing or decreasing is we compute that derivative and set it equal to 0. So we've got y prime. We're setting that equal to 0. We're solving for x. Solve this equation for x, we can factor it. These two terms have a 3x in common. 3x times x gives us a 3x squared, and 3x times a negative 4 would give us that second term. And so you've got this factor times this factor equals 0. The only way that happens is if this factor equals 0 or this factor equals 0. Then if we solve this equation for x, we get x equals 0. We solve this equation for x by adding 4 to both sides, we get x equals 4. So these are two x values that are critical values for our function. These are potential x values where this function could change signs. It might go from positive to negative or negative to positive, but it's also possible that it goes from positive to positive or negative to negative. It really just depends. But these are our critical values. Now, one way that we can sort of do some bookkeeping for this to keep track of the intervals where the function is increasing and decreasing is to make what's called a sign chart. So we draw a number line here. And then we list our critical values on the number line in the appropriate order. Now, remember, we set y prime equal to 0 and solve for x to find some of the critical values. We should also look for any values for which the derivative is undefined. In this case, the function is well defined all the way. If there are any x values where the derivative is undefined, those are critical values as well. Say no in this case. So these are our only critical values. And then our y prime is actually a product. It's a product of these two factors, 3x and x minus 4. So I like to list my factors here and then look at the sign of each of these factors on each of these intervals. So this is a number line, so it goes from negative infinity to positive infinity. And we're saying, okay, if x is on the interval from negative infinity to 0, what's the sign of 3x? Well, if we're over here, x is a negative number, so it's 3 times negative the negative number, so we get a negative value. If we're on the interval from 0 to 4, so x is positive, 3 times x will be positive. From 4 to infinity, our x value is positive, so 3 times that positive number is positive. Now x minus 4 is going to be positive when x is greater than 4. So you could just choose an x value. Say x equals 5. 5 minus 4 is 1, which is positive. No matter what x is, if it's in this interval, that number minus 4 is going to be positive. Now, if x is between 0 and 4, we're going to get a negative number. So choose x equals 3, let's say. 3 minus 4 is negative 1. 3 minus, or if we chose x equals 1, instead we have 1 minus 4, which is negative 3. It doesn't matter. Any x value that we choose in there, we're going to get a negative value because that number is actually less than 4. And if we have x equals a negative number minus 4 is going to be a negative number. And y prime is the product of those. So on the interval from negative infinity to 0, y prime is a positive number, or excuse me, a negative times a negative, which is a positive. And then on the interval from 0 to 4, y prime is a positive number times a negative number, which is negative. And then on the interval from 4 to infinity, our y prime is a positive times a positive, which is positive. So that tells us that y prime is positive on this interval, negative on this interval, and positive on that interval. And we know that the slope is 0 at x equals 0 and 4. So our function goes from increasing to having a 0 slope to decreasing. And then at x equals 4, it goes from decreasing, having a 0 slope, to increasing. So at this location, we're going to have a relative max, and at that location, we're going to have a relative min. And the function's derivative is positive here and here. So those are the intervals where the function is increasing. And this on this interval, when the derivative is negative, our function is decreasing. So the question says, find the intervals where f is increasing. So y equals x cubed minus 6x squared plus 15 is increasing on this interval and this interval. So negative infinity to 0 and 4 to infinity. And the same function is decreasing when the derivative is negative. So it's decreasing on that interval there. And because it's going from increasing to 0 slope to decreasing and decreasing to 0 slope to increasing, we have a relative max there and a relative min there. That's called the first derivative test. So since our derivative changes from positive to 0 to negative, we're going to have it's increasing, then it's 0 slope, and then it's decreasing. The function value at 0 is a relative max. And since our function f prime changes from negative to positive at x equals 4, the function goes from decreasing to having a 0 slope to increasing. We know f of 4 is a relative min. Now, with this information and these two pieces of information, we can graph our function if we want to. But that's not what we were asked in this question. We were just asked to find the intervals where y was increasing or decreasing. So we've already answered that question. If we want to, we can confirm this graphically. So let's confirm that graphically on desmos.com. And then we'll also see that our conclusions here are accurate. And again, this is something that's called the first derivative test. And I will outline that more explicitly after we look at the graph of this function. So here's our function. We can see that the function is increasing from negative infinity to this x value. And then it's decreasing from this x value to the x value at this location. And then it's increasing at the end. So it's increasing, then decreasing, and then increasing. Now that x value can be found by computing the derivative function and then setting that derivative equal to 0. Well, we see that the derivative is 0 when x equals 0. And the derivative is also equal to 0 when x equals 4. So the intervals of interest are negative infinity to 0, 0 to 4, and then 4 to infinity. Now, when we created our sign chart, we saw that the product of 3x and x minus 4, which is how this factors, is the product of a negative and a negative on this interval, so it's positive. We can also just read the graph. If we look at f prime, we can see that the function values for the derivative are positive from 0 to infinity, which is consistent with the graph of the original function. We see that the graph is going up as we go from left to right on the orange function. And then on the interval from 0 to 4, we see that the y values on the graph of f prime are negative. So those derivative values should be negative, and the derivatives are negative. All those tangent lines are going to have negative slopes between 0 and 4. And then from 4 to infinity, our slope goes from 0 up to positive infinity, and it just keeps increasing. This graph of f prime can allow us to infer that the function is increasing here and then decreasing here because f prime is negative, and then increasing here. So that's consistent with the picture of the original function. Now, if I sketch each of the branches where x is less than 0, and then where x is between 0 and 4, and where x is greater than 4, say on these purple branches, our function is increasing. And on that middle branch, or it's not really a branch, on the purple parts of the function is increasing. And on that blue part of the function is decreasing. If I want, I can label that point at the top and label that point at the bottom. This is a relative maximum, but I want you to be very careful when we talk about a relative maximum. We have a relative maximum at this location because the function goes from having an increasing slope to a 0 slope to a decreasing, or not an increasing slope, positive derivative to a 0 derivative to negative derivative. So the function goes from increasing to having a 0 slope to decreasing. Whenever that happens, we have a relative max. Now, a relative maximum is not a point. It is not an ordered pair. The maximum value of the function occurs at x equals 0, but the relative maximum of the function is actually the y value. It's y equals 15 at that location. And over here at x equals 4, we have a relative minimum. Because the function goes from decreasing to having a 0 slope to increasing again. Since that derivative is changing signs, we've got a relative minimum. But the relative minimum is not an ordered pair. The relative minimum is actually the y value at that x value. The x value at x equals 4 is the location of the relative minimum, and the relative minimum value is negative 17. This particular function on the entire real line does not have an absolute min or an absolute max. because the function's range is negative infinity to infinity. But we do have this relative max of 15 and a relative min of negative 17. And identifying those using the signs of the first derivative is called the first derivative test. So we will look at that more, I think, in another video. But that's the idea. We have identified the intervals where f is increasing and decreasing. Let's actually state those intervals. Say f is increasing on negative infinity to 0 and 4 to infinity. Now you always have intervals of x values where the y values are going up. And f is decreasing on the interval from 0 to 4. Okay, and then since the sign of the derivative changes from positive to negative at x equals 0. So we have the function's increasing, then it has a 0 slope, and then it's decreasing. F of 0, which is 15, is a relative maximum of the function. And then similarly, since the sign of the derivative changes from negative to positive at x equals 4, the function is going from decreasing to having a 0 slope to increasing. F of 4, which is negative 17, is a relative minimum of the function. And then if we were asked for absolute extrema, we'd say since the function has a range of all real numbers, the function does not have an absolute maximum or an absolute minimum. We can make the y values on that graph as small or as large in magnitude as we want, either positive or negative, because the range is all real numbers. All right, so that's how we do that. I think we'll stop there. In the next video, we'll do another example, and we'll also sort of make that rule, for the first derivative test, a bit more concrete.